Hello and welcome to this lecture. In this lecture, we're going to particularly focus on two specific types of functions. One of the form x power a, sort of like the power function, and the other of the form a power x, which is sort of like the exponentiation function. Okay, so both of these functions we will look at in pretty good detail and see how to work with them in some sense. Okay, so that's going to be the main purpose of this lecture. So if you remember, you now know how to do exponentiation of different types, powers and exponentiation we know how to do. So given that we know that, these functions are a natural next step to study. Okay. So just one quick important caution, which maybe I didn't mention very explicitly. So I've been talking about computing the sth root or a power 1 by s. So by the way, this a power 1 by s is called the sth root of a. Okay. So for these computations, I've been making one implicit assumption, which maybe I didn't clearly specify, and some of you may be confused by that. When I'm computing the sth root, I'm assuming a is positive, first of all. I'm not doing it for a negative. A negative is too complicated. And then also, I'm focusing on finding the unique positive sth root. Okay, so I'm not interested in all the sth roots of a, or sometimes it has negative roots and all that. All those things I'm not interested in. I'm going to focus. So far when I've been computing a power 1 by s through these sequences, I'm limiting to a being positive, and I'm interested in the positive sth root. Okay, negative sth roots exist in some cases when s is even, and in fact, if a goes negative, real sth roots may exist sometimes when, particularly when s is odd, right? And then there may not be a positive real root and all that. All sorts of different cases arise. It's not that complicated, but nevertheless, we have to consider all these cases. So instead of doing all these cases in detail, I'm just saying I'm going to compute a power 1 by s when a is positive, and I'm focusing on the positive sth root. So this is something I've been assuming, though I didn't make it very clear. I hope this clarifies it. So the general case of computing the sth root is a very interesting problem, and I will urge you to wait till we study complex numbers in this class, and at that time we'll come back and revisit this problem in more generality. Okay, so that's a quick caution. So let's proceed. So if you recall, for any function, when we studied any function, we were interested in three basic tasks. You should be able to compute the function, you should be able to plot the function, you should be able to invert the function. So more or less, if you can do these three, you can do most tasks that you have to do with functions. At least these are basic tasks, and we should be able to do them. Okay. First thing is, let's focus on the compute part. Both x bar a and a bar x, given a and x, we know how to do this, and in many cases it may be easy. But in some cases, you may need limits of sequence of rationals, and we've seen extensively how to do this, so we know how to do this. Both are nice tick marks. But plot, we have not seen it yet. Maybe it's easy enough, but we don't have a sense of the plot. How does x bar a look? How does a bar x look? How do they compare with each other, etc., etc.? We have not seen it. And finally, if you look at inverting x bar a is not too bad. You can, so you know what is inverting. Well, basically, given y naught, find x naught if y naught x naught such that y naught equals f of x naught. So basically, find an x naught which, when transformed through f, will give you a y naught. So that's like the inverse problem of computing the function. And at some level, it's not too bad. You can just do y naught power 1 by a and wonder whether the ath root will exist for y naught or not, and if it exists, how to compute it, etc. Maybe you have to do a sequence. I'm going to put a tick mark here. It's sort of like a qualified tick mark, because it's sort of a similar x bar a type computation. It's a computation which we've seen before, except existence and all that you may have to worry a bit. But I'm going to sort of not go there in detail and say that the invert problem even for x bar a is done in some sense. Okay, but this problem, the inverting for a bar x, is still not done, right? So we have not seen this inverse of a bar x. From your experience, you may know involves a function called the logarithm function, and we have not introduced that in this class yet. So these three things have not been done. So we're going to tackle the plot problem mainly in this lecture. Okay, so we won't do the inverse now. We will plot these x bar a and a bar x for different values of a, and then compare them. Be comfortable with these plots. So I've seen in my experience a lot of students learn these functions, but they're not able to plot it or not able to visualize it. they're not able to understand and compare and all that. So these are very important. Even as an electrical engineer, electronics engineer, later on you will meet these functions often for different values of a power x and different values of a x power a, and you should have a sense of how these things behave in terms of the plot. So we'll go through the plot. I'll briefly describe how they look, and then we'll proceed. Okay. So here is a big plot of x power a versus x for a positive and x greater than 0. I've plotted a bunch of things. They all sort of looks like a, like an onion, or I don't know how else you can call it. It's like something that's shooting out like that. It's a bit of an interesting plot. What I've done here is simply for a positive. Okay, I've not looked at, of course, a negative and all. We're not going to see. We will see maybe later. But x power a for a positive and x also positive. Now see, if x goes negative, then negative number power something and all is a bit complicated for us. So we're not going to look at that. So x is positive, a is positive. Let's first try and understand that, right? So how will that look? And here are a whole bunch of graphs. So instead of just walking you through these graphs, what I'm going to do is let's try and see if I can, get out of full screen mode here and take you to Desmos, and then do this plot of y equals x power a. Okay, then I'll add a slider for a. Okay, and then a is 1 and y equals x is this line, right? So it's very nice. It's no problem here. Maybe let's zoom a little bit so that we get a interesting curve. So notice what's happening as I increase a. As I increase a, so maybe let's see the problem. One of the confusion is to not do x negative. So let's not worry about x negative. So come here. So that's nice. So now as I increase a, notice what happens. Something very clean we can talk about. Oh, I shouldn't go a less than 1. So a is 1. I'm going a greater than 1. Notice what happens here. So it is sort of becoming, it's increasing more and more sharply, and it is bending down, bending in different ways, right? So between 0 and 1, it seems to be bending below in this fashion. After 1 onwards, it is sort of taking off in another fashion. So hopefully you can notice the difference here. So this is what's going to happen. But some things are remaining the same, right? So if you look at the 1, 1 point, the 1, 1 point, right? This green dot here. So maybe I should put a label there. Whatever I do to a in the positive direction, it is in this direction or any other direction for greater than 1, it is passing through 1, 1, right? So notice this plot is always passing through 1, 1, and of course 0, 0, right? At 0, 0 also it passes through, 1, 1 also it passes through. And as I increase my value of x, some interesting thing is happening. Something is happening in 0 to 1, and something is happening above 1 for x. Okay, and these two seem to be a bit different as I increase a. Okay, now if I go below 1, okay, if I go below 1, notice what happens here. Okay, maybe I should do 0 to 2 in steps of 0.01. So this might be a little bit more interesting. So it will give me more values here. So at 1, I have a straight line. As I go to the right, it is sort of tilting in this way. Notice what happens when I go to the left. It is tilting the other way, right? So you see it sort of goes, if I go to 0.5 and all, it's sort of tilting in the other direction. So when I increase beyond 1, it tilted in a different direction here in this fashion for 0 to 1, and then it was going up like that. And then when I'm going below 1, it's sort of increasing in 0 to 1, then sort of decreasing in this fashion. But always it goes off to infinity eventually. Even if I go to very, very low values, eventually it goes to infinity. But it has this kind of a shape, right? So notice the difference between like a being less than 1 and a being greater than 1. A being greater than 1, it has this kind of a shape. And then a being less than 1, it has that kind of a shape. The shape and the thing sort of changes. And whatever I do to a, as long as it's positive, I see 1, 1. It always passes through 1, 1 and 0, 0. Okay, so that's not very surprising. That's how this y equals x power a will behave. Okay, so I hope when you just sweep through these things, and convince yourself that you're happy with this. Maybe this 2 can be, okay, 2 can be a bit bigger, maybe it can be 20, right? So we go above, go all the way to 20. Notice what it does. It just seems to be very stubbornly steeply climbing. The rate at which it climbs seems to change a lot. It's interesting, isn't it? When you go all the way to 0, it becomes a flat line, y equals 1. So sort of starts from that flat line and wants to go towards that vertical line, which of course it cannot reach. And then there is this wonderful case of a equals 1 in the middle, which is the y equals x straight line. Okay, so a lot of nice illustrations here. I hope this is interesting to you. So I'll urge you to play with Desmos yourself, try all these things, then this will give you a good picture of what's going on. So let me come back to the screen here, the presentation, and then go maybe into full screen. Okay, so what I've done here is I've done all these different Desmos plots for different values of a. You can see the purple one down below is y equals x power 20, and then I have y equals x power 5, then I have y equals x squared, then the black one is y equals x. The red one is not labeled, it is some x power, I think 1 point something or something like that, okay. And then above y equals x, you start seeing the case of a being less than 1. So you have root x, which is x power 0.5, then x power 0.25, then x power 0.07. So you see, if you think of y equals x as sort of some sort of a middle line here, as I increase the value of a, right, if I go above 1, I'm sort of, in 0 to 1, I'm going down, but notice what happens in above 1, right? So notice this x power 20 is the steepest curve. This guy is x power 20. He's going way above here. And then you have x power 5, then you have x squared. So when x is greater than 1, you know, the exponent, the larger exponent goes higher, right? When x is less than 1, right, the larger exponent goes very low, right? And that's sort of clear, right? So because when x is less than 1, x power 20 is going to be much smaller than x power 5, right? Because I'm multiplying with some fraction over and over again 20 times. So it's going to go much lower. But on the other hand, when x is greater than 1, x power 20 will be much, much larger because I'm multiplying something greater than 1 over and over again 20 times. So you'll get a much larger number, right? On the other hand, as you decrease the power, this behavior changes. So this around 1 is this critical way in which this behavior changes for x power a. Okay, so you get this nice, if you put all of these things together, you get this nice onion, or I don't know, what else can you call it? Is it like a flower pot? I don't know, during Diwali time, a tilted flower pot, maybe it's that, okay. So that's what this is, and here are some observations. It passes through 0, 0 and 1, 1 for all a. For large x, eventually becomes large and unbounded for all a. Whatever your value of a may be, eventually, as you increase x higher and higher for large values of x, this function will go unbounded for any a. Whatever a you may pick, this will go unbounded, okay. So I've made this behavior a bit more precise. If you fix a particular x and that x value lies between 0 and 1, for x lying between 0 and 1, if your exponent is larger, okay, then the value goes smaller, right. So if the lower exponent, a naught less than a1, will have a higher value. And the same behavior will reverse when you go x greater than 1. When x is greater than 1, if your exponent is larger, you're the king. So you become larger because you're multiplying by something that's greater than 1. So if you multiply more, you will get something larger, okay. So this is true no matter whether a naught and a1 are integers or not, etc. Whatever the value is, this would be true, okay. So this is a good way to remember this x power a function, this flower pot like picture with its inverted behavior between 0 to 1 and greater than 1, okay. So that's x power a for one particular case. What about a being negative? What about other values of x? Okay. So here is a plot where I've gone to all x here, not just x being positive, all x, but I've restricted a to integers. Why have I done that? If a becomes a fraction, then I will need, like, you know, r by s or something in the power, and if x goes negative, then I don't want to get into the business of 1 by s root of negative numbers, right? So to avoid all that, I'm going to say a is an integer and I'm going to look at all x. Okay. So let's try these plots here. I'm going to go and try this in Desmos and then come back and show you what happens. Okay. Let's try this in Desmos. So y equals x bar a. I'm going to do all x, and then this guy is going to be 1, 2, 3, etc. and step is going to be 1. Okay. This is, let's start with y equals x. This is like a equals 1, so this is y equals x. And then as I go to the next step, when a becomes 2, I get this nice parabolic type shape, y equals x squared, right? So you see this on the left hand side, because y is x squared, you can see that it has this u type of shape. There is some symmetry here because it's x times x, right? Whether x is positive or negative, you get the same value. So 1 at 1, for instance, even at -1, you get the same value evaluated. For at 2, x square is 4, -2 also x square is 4. Because of this even power, it becomes symmetric about the y-axis, right? So you get the same picture. Now notice what happens when you go to a equals 3. You get a dramatically different plot. Okay. So the plot on x bar 3 sort of is similar to x bar 2, except it rises a little faster above 1 and falls a bit more below 1. But other than that, it's okay. It's similar to that. But then for x negative, because it's x cubed, it has this odd symmetry. So it doesn't reflect about the y-axis alone. It reflects about the y-axis and then reflects about the x-axis also. So that's what you do here. So notice the difference between a equals 2 and a equals 3. I hope you appreciate that. So here there is a reflection about the y-axis and you get this symmetry. That's all. Now when I went to 3, it's like 2 reflections happen, right? It goes y-axis and then x-axis again, because when x is negative, like for instance -1, x cube is going to be -1 again. Okay. So it has to go to this side, right? So it will be minus of the positive value. Okay. So because of that property, for odd a, you will have this kind of behavior. So this will repeat now. If you go to a equals 4, see again you get this u type of function, but you can see that it is lying, it's flat around 0 for a longer time, like typical behavior, right? When you increase the exponent, it's flat around 0 for a longer time, longer width, right? You can compare a equals 2 with a equals 4. 2 seems to have a very short width around 0, but if you go to 4, you're getting a bigger width, because values close to 0 will become even smaller when you raise to the power 4. And then the rise is steeper. Look at this rise for a equals 2 and a equals, so it's more shallow, no? It's rising more shallow. If you go to a equals 4, the rise is much sharper. Okay, so it stays like, it becomes like a proper tumbler kind of thing. So it wants to become a tumbler. So as you go to larger and larger values, the same thing will repeat. You go to a equals 5, again you see, it's a bit more, it stays at 0 longer, rises steeper, but then it doesn't have the symmetry just about the y, it goes below x also. So that's the kind of shape it will get. And then for 6, again, the same, more of a tumbler behavior, and 7 goes to, this inverted behavior. So you notice this back and forth between odd and even, and as you increase the exponent, it's going, it's showing that sharper difference. Okay, so if you go on increasing, so notice this tick, 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 going up and down and up and down. Let me show 19 here. So you see it's almost flat for a long time, and then it rises steeply. Go to 20, it's long, it's flat for a long time, and then it rises. Okay, so that's how this picture. I've tried to capture that here. I've put so you see for all the even values, you're getting these pictures that are on top, and then for the odd values, you're going in the odd symmetry way. So here are a few points. All the curves pass through 0, 0 and 1, 1, and all the curves for large positive x go to infinity, right? For large positive x, they go to infinity. They go off to infinity. If a is even, all the curves pass through -1, 1. And for large negative x, it goes to plus infinity. And then there is this even symmetry. Minus x power a is x power a. So it's even symmetry. If a is odd, it passes through -1, 1. and for large negative x, it goes to minus infinity. Okay, and then the odd symmetry behavior minus x bar a is minus x bar a, so it goes from first quadrant to third quadrant directly. Okay, so that's the behavior for x bar a for a being integer, all x positive and negative. So here is a picture of x bar a versus x when a is minus 1, minus 2, so on, and all x. Okay, so once again, let me go to Desmos, then change my a to go from minus 20 to minus 1. Okay, so that's the picture here. So this is a equals minus 1. Let's look at this plot now. This is a new plot that we are seeing. So when a is minus 1, you have 1 by x. Okay, so this plot is actually the plot of 1 by x. So what happens to 1 by x? How will 1 by x look? It has a curved and continuous sort of shape, and that's maybe okay. It passes through 1 comma 1, that also may be okay. What happens for very large x for 1 by x? We've seen it, we've seen that this 1 by n tends to 0, right? So likewise, this 1 by x also, as you go to larger and larger values of x, it's going to go off to 0. So it will slowly eventually get to 0, right? So this is how it will look. But as x approaches 0, 1 by x will shoot off to infinity, plus infinity, right? If you go closer and closer to 0 on the positive side, 0.01, 0.001, 0.0001, 10 power minus 18, minus 19, minus 200, whatever, 10 power minus 200. If you keep doing that, it is shooting up, right? If x is 10 power minus 200, 1 by x is 10 power 200. So it's just really shooting up. So this kind of a picture is what you will have for 1 by x. And interestingly, because 1 by x is like an odd function, this, if you put x equals minus x, you get minus 1 by x, it will sort of get a reflection into the third quadrant, and you will get a picture like this for 1 by x for x negative, right? When x is negative, 1 by x is also negative. So when x is negative and close to 0, it shoots off to minus infinity, and if x becomes very large and negative, it eventually goes down to 0, okay, or goes up to 0 in this fashion. Okay, so this is how 1 by x looks. If you do 1 by x squared, which is what is this guy, this is 1 by x squared. Okay, a became minus 2, so 1 by x squared. So on the first quadrant, 1 by x squared seems to be sort of reasonably similar to 1 by x, except that the fall here as it goes to 0 is sharper. Okay, so you see here, this is a bit more shallow, there's more gap here. When you went from minus 1 to minus 2, this gap became lesser, right? So the fall to 0 is faster here. And likewise, the rise to infinity will also be faster here. So you look at this. This is going a bit more slowly. This one will go much more rapidly. Okay. So, but on the other hand, when it's okay, it goes through 1 comma 1, it's falling to 0 as x becomes large. It's going off to infinity as x becomes extends to x goes towards 0. That's okay. All those things are fine. But critical change between 1 by x and 1 by x squared is the symmetry, right? 1 by x squared when x is negative is also positive. Okay, so because of that, it just goes off to plus infinity. It doesn't have that third quadrant type behavior. It's only second quadrant. Okay, so it goes off to infinity whether x is positive or negative. Okay, close to 0. As long as it's close to 0, it shoots off to infinity. Okay, it has that kind of behavior. And now we can keep going, you can go to 1 by x bar 3. Once again, the same behavior, you see, it falls sharply to 0, then shoots off sharply to infinity, and then the same behavior will continue. X bar 4 is going to be symmetric, odd, even symmetric, and same sort of behavior. As you keep going, you go all the way to minus 20, you see it's a very sharp fall to 0 and sharp increase. And if you do minus 19, it's going to show you the other thing with the similar type of behavior with third quadrant. Okay, so I hope this sort of gave you a feel for how x bar a will look for a negative integer and all x. The reason why when I don't want to consider all x and x being negative, because if a goes into a fraction non-integer value, then I have to do these s roots, and that doesn't work for x properly. Okay. So that's this picture. So I've drawn a few of them here for you. 1 by x, you can see, comes here 1 by x bar 5 is this green curve. on first and third quadrant, and 1 by x squared is the blue curve, first and second quadrant, and then the purple curve is 1 by x power 10, which is first and second quadrant again. Okay. Some of the properties: passes through 1 comma 1 always. For large x it goes to 0 always, whether it's positive or negative it doesn't matter. For large x it goes to 0. A is even, there is some behavior, the symmetry and all that, and it goes to infinity at 0. And A is odd, it goes to minus infinity. For negative x close to 0, for positive x it goes to infinity anyway. Okay, and then this odd symmetry. Okay, I hope this is clear now. So I think this is the last slide on x bar A. So x bar A, we now have these three different plots: this flower pot type plot, and then these tumbler like plots for even, and then this sort of weird other twisted tumbler for odd functions. And then when you have a negative, an integer, and then you have this going off to infinity and then going down to 0. It's a different behavior to the other one that we saw. Okay, so these pictures are good to keep in mind. I think these give you a good feel for how x bar A behaves. Okay, now that we've seen x bar A, we're going to see a power x. Okay, so this is the second type of function, and a power x also you can start out once again with Desmos, which is our wonderful here. So y equals a power x, and then a can go 0 to 2 maybe, and we can keep the step as 0.01, maybe 0 to 20. Okay, there you go. So I don't know why it's refusing to. Okay, so there you go, y equals a power x, and okay, a equals 1 is a good place to start. If a is 1, you simply get y equals 1, right? Is that okay? So if a is 1, you get y equals 1, and then as you increase a, notice what happens here. So you get this kind of a curve. So this is a very typical exponential curve. Okay, it goes in this fashion: a power x. You can look at it when a is positive. A power x is always positive; it never goes negative. And then it just shoots off really fast to a very large value. And when a is greater than 1, I'm talking about. And then when x is negative, when a is greater than 1, it falls off again very rapidly. Okay, so if you increase the value, so you see here, by the time it gets to something like 20, it is quickly falling off to 0 and then increasing rapidly exponentially. Okay, so that's the behavior for a from 1 positive. Okay, positive greater than 1. I'm sorry, most important is it's being greater than 1. You should also play with it and see what I mean. When a is greater than 1, this is the sort of behavior that you get. Okay, the exponential, typical exponential behavior. Notice the 0, 1 point was always on, right? As in, it will always pass through 0, 1, and when x is 0, it will always be at 0, 1, and then the shape sort of twists and turns. And I want to tell you again, you see this kind of a turn, right? When you see this kind of a turn, the behavior for less than 0 and greater than 0 is different. As a increases, if a goes from say 6 to 12, you see the values on when x less than 0 have gone down, but on the other hand, for x greater than 0, they've shot up. Okay, so this different behavior is there around 0 for this guy. Okay, so let's change the range now. Instead of going above 1, let's go 0 to 1, below 1, and let me keep the step size the same. That's okay. Okay, so it's below 1. Notice what happens when it goes below 1. Ooh, it turns completely in another direction. So notice how, so by the time you come to like 0.5, let's say 0.5 power so let me just remove this, I'm sorry. We are doing a power x here. 0.5 power x, notice this behavior. It's got like an exponential behavior, but reversed. When x is positive, it is falling. It's 0.5 power x, right? So less than 1. So what you're raising to the power is less than 1. The base is less than 1. So when you keep raising to higher and higher power, it will fall off to 0. On the other hand, if x is negative and your base is less than 1, it's going like 1 by 0.5 whole thing raised to the power, a positive number. So it's like 2 power x. So it's sort of going off in exponentially high in this direction. So hopefully you see that when a is greater than 1, it has this kind of an exponential behavior. When a is less than 1, you have a fall behavior. Okay, so those two things are a bit away from each other. So I hope this picture is clear to you. A less than 1 will have this kind of an exponential behavior, and as I keep reducing value, it has this, it moves in this sort of fashion. Okay, so I hope you can see this. When I increase value from 1 onwards, as I decrease it, it sort of sharply goes. Of course, when I go to 0, it will be it should not be 0. But as you get close to 0, you get this kind of a behavior. Okay, sharp exponential rise on the negative side because a is less than 1. Okay, so here what I've done in this picture for you is for a greater than 1, when I know my exponent is in this fashion, my exponential rise is in this fashion. Okay, I have a greater than 1. I have different curves here. So you see y equals x. I've just drawn y equals x for comparison, just to show you how the exponential behavior is really high. It takes off in a very different way. And you see here lots of interesting things about y equals x. 1.2x will even go below y equals x, by the way, like this. While of course it will quickly overtake y equals x, and it will go above it right here. And then there's 1.4446, and you can look up what this is and what is so special about this black curve. I'm not going to talk in detail about it. It has just one intersection here. After that, the intersection stops, and all of them pass through 0, 1, right? And for large positive x, they go to infinity. For large negative x, they go to 0, because a is greater than 1. So that's very important. And then comparison wise, if x is positive, a power x is always greater than 1. Okay, so that's also important. For positive x, it's greater than 1. For negative x, it's less than 1. Okay, so that's what happens if a is greater than 1. So that you can see in this picture quite easily. And if x is positive, a larger base means a higher value. Okay, and when x is negative, a larger base means a lower value. Okay, so that also you can see the base of this exponent a, as it increases, if x is positive, it shoots up so much higher. By the same token, if x is negative and if the base is higher, it has fallen very rapidly. Okay, so that's the sort of shape that this takes. Okay, I hope this plot gives you some idea of how a power x behaves. Of course, you'll have to go and try it on Desmos yourself, look at some of these plots and really get a feel for what's happening. The same thing I've done for a less than 1, a from 0 to 1. And the crucial property is this symmetry. Okay, so look at this sort of symmetry. I'm calling it a symmetry here, but the base changes. If you have a power minus x, it is sort of symmetric to 1 by a power x. Okay, so a is less than 1, so 1 by a will be greater than 1. So if you want to do a power minus x, it's 1 by a power x. Okay, so or a power x is 1 by a power minus x. So you take 1 by a power x and then flip it around the y-axis, you will get a power x. Okay, so that's the idea behind this symmetry. So everything will do like this reflection about the y-axis. Whatever we had here, you reflect about the y-axis, you will get this picture. Okay, so you see here 1.2, this 0.833 is 1 by 1.2. Okay, likewise here 1.4466, sorry, and 0.692 is 1 by 1.44. Here you have 0.5 power x, and I'm sorry, and then this became 2 power x, and then 20 power x, this is 0.05 power x. So I've just done the 1 by a to get a reflection here, and that will work out in that fashion. Okay, so it passes through 0, 1 always. For large positive x, it goes to 0, right, when a is less than 1. For large negative x, it goes off to infinity. Okay, and if x is negative, it's less than 1. Okay, I think this one is wrong here. Okay, so there's a bug here in this. I hope I've corrected it. If x is negative, when a is less than 1, when x is negative, a power x is going to go above 1, and when x is positive, a power x is going to go below 1. Okay, and then the same way the base and the comparison. So if the base is going to be higher, and the value will be lower for negative x, and if the base is going to be higher, the value will be higher for positive x. Okay, so that's how this behavior works. Okay, so these things, I'm just showing you, but you have to really play with Desmos to understand how these plots look and convince yourself that you've understood. Okay, so let's come back to our basic tasks here. So we have computed, we know how to compute, we know how to plot, hopefully, right? So we have a good sense of how the plots for x bar a and a bar x look. Invert for this x bar a we already know, but this one is still an x. We don't know how to invert a bar x yet. We have to learn that officially in this class later. Okay, so this sort of summarizes x bar a and a bar x for you, and we'll move on to other interesting topics in later lectures. Thank you.